Hi everybody, hope all's well. We're continuing today with section 6.2. 6.2, slide 88, page 44 of your notes. So last week, or last time we met rather, we discussed what angles are and how to properly measure them. Now we're going to put them in context. So we're going to put angles in specific scenarios and try to see what trig or trigonometry is really all about. So 6.2 begins to scratch the surface. What 6.2 deals with is trigonometry of right triangles. So firstly, what is a right triangle? Before we get into anything on slide 88, a right triangle is a triangle that has one angle equal to 90 degrees. One right angle, the angle that's equal to 90 degrees, in a three-sided shape or triangle, makes a right triangle. Now, why is this equal to 90 degrees? Last week we discussed what a degree measure is, and basically 1 degree would be, if we put a standard axis together, XY axis, we have a rotation of one ray out of 360 parts. So 360 degrees is one complete revolution. I can go 2 complete revolutions, 3 revolutions clockwise, I can go counterclockwise, all things we discussed in 6.1. Here, if we go 90 degrees, we're going a quarter of a revolution. That's this angle formed here, right? Between these two rays. Sort of like an L shape. So that's a quarter of a complete revolution. A quarter of 360 is 90. If I have a 90 degree angle in a triangle, it's a right triangle, and then I can apply one of these 6 trig ratios. What are trig ratios? Well, here we say, consider a right triangle with theta as one of its acute angles. Acute doesn't mean it's pretty, right? Acute means an angle that's less than 90 degrees. So if I have one angle that's 90 degrees, both of the other angles would be less than 90 degrees. Because 90 plus 2 other angles have to equal 180. So these 2 angles have to add up to 90. By definition, both being less than 90. So if I call theta, or theta 1, the acute angle within this triangle, one of the 2 acute angles, I could then define 6 trigonometric ratios: sine, cosine, tangent, cotangent, secant, and cosecant is the order on your slides. And all of those trig ratios represent a relationship. Just like a function beforehand was a rule, a trig function is also a rule. If I take the sine of an angle, the input to this rule is an angle measure. The input is an angle. The output is going to be a ratio of sides, or a comparison of sides. For the sine of an angle, the sine of the angle is going to be the opposite side over the hypotenuse. Now, depending on the angle drawn, here in this triangle, and this theta being my angle, if I took the sine of theta, this angle, that would be equal to, so the sine of this angle, regardless of what the angle is, I didn't tell you what the angle was, if it's 10 degrees or 20 degrees or 50 degrees, the rule is that the sine of this angle would be the opposite side, so the side opposite the angle would be the opposite side, and the hypotenuse is always the side opposite the 90 degree angle. It is the longest side. So if I took this side measure and divided this over that, I would have the sine of the angle. Cosine is adjacent over hypotenuse. Adjacent is the side that is right next to the angle that is not the hypotenuse. So adjacent means next to, right? So if you look at angle theta, this side is adjacent and this side is adjacent, technically. But they're not both considered the adjacent side because one of the sides is the hypotenuse. So this would be the adjacent side to this angle. Now it's very important to note, if I drew out a similar triangle here, and I looked at it from the perspective of this angle being theta, well, this would be the opposite side, this would be the adjacent side, and this would be the hypotenuse. Because again, adjacent means next to, this one is next to this angle, and this one is next to this angle, but this side is opposite the 90-degree angle. That trumps it, so that makes it a hypotenuse. Now, some of you might ask, well, that's fun and good. What if you didn't put theta here? What if I put theta there? So, take a look at this picture. It tells you that this is the adjacent side, that's the opposite side of the angle, and this is the hypotenuse. Well, if theta was drawn here instead, that would change some things around, but not everything, right? Now, adjacent to this theta are these two sides. This side is still the hypotenuse, though. So this wouldn't have changed. This would stay hypotenuse. But now, if this is theta, this becomes the adjacent side, the side next to theta, and this becomes the opposite side. Okay? So, the naming convention depends on what angle we're looking at, but the way we think about it is always the same. Opposite is the side opposite the angle we're talking about. Adjacent is the side right next to the angle we're talking about that isn't the hypotenuse, and hypotenuse is always the side opposite the 90-degree angle. So what the sine of an angle is, the sine of theta, would be the opposite side divided by the hypotenuse side. And this is weird because we're taking an angle measure, and we know that the three angles in a triangle sum to 180 degrees. So this angle plus this angle plus this angle add up to 180 degrees. We're going to get to a relationship that portrays the two sides and the hypotenuse soon enough in this lecture. But what the trig ratios are going to do are relate the angle measures to the ratios of sides. So the sine of the angle is the opposite over the hypotenuse. The cosine of theta, as you see in your slides, is the adjacent side over the hypotenuse. The tangent of the angle is the opposite side over the adjacent side. Then we see three more ratios. We see the cosecant. So the cosecant of the angle is 1 divided by the sine of the angle, which we'll get to reciprocal ratios soon enough. But what that will tell me is, and you see it in your slides, that it's the hypotenuse over the opposite. So it's the reverse or flip of the sine. That's cosecant. Then we see secant of theta, which is the reciprocal of cosine of theta. It's the hypotenuse over the opposite. Hypotenuse over adjacent. Again in your slides. And then the cotangent of theta, which is the reciprocal of tangent. Adjacent over opposite. A over O. All of that in our slides. How do I remember this? Well, we see the first three are shortened to SOHCAHTOA. I'm sure some of you guys have gotten this at some point in your lives. SOHCAHTOA is sine, S is opposite over hypotenuse. That's the SO in SOHCAHTOA. Cosine, C, is adjacent over hypotenuse. That's the CAH. C-A-H. And tan is opposite over adjacent. That's the TOA. SOHCAHTOA helps us with the first three. So the tangent of this angle is TOA. Tangent of theta is the opposite side over the adjacent. The cosine of this angle is the adjacent over the hypotenuse, CAH. The first three are easy to remember because of SOHCAHTOA. The next three I have a short little thing that helps me remember it. The sine of theta. So sine starts with an S. Its reciprocal function, cosecant, is going to start with a C. So I go from S to C. So if sine is opposite over hypotenuse, the reciprocal function cosecant will be the reciprocal, hypotenuse over opposite. S maps to C. What about cosine? Cosine starts with a C. Its reciprocal function starts with an S. So S goes to C, C goes to S. This is adjacent over hypotenuse. Secant is hypotenuse over adjacent, the reciprocal function. Tangent and cotangent both have a tangent in them. So that's how I remember that one. Tangent and cotangent both have a tangent. So cotangent is the reciprocal of tangent, and tangent you remember with TOA. So for all of these, what is common? If I were to ask you to evaluate the secant of theta, the secant of some angle, you would then find the hypotenuse length, divide that by the adjacent side length. That's how you evaluate it. To get the sine, cosine, tangent, secant, cosecant, cotangent of an angle, we find the ratios of sides. Next slide. You might have a question, well, what if the triangle is bigger or smaller, and how do I necessarily evaluate? Can you give me an example? Well, fine. If this was 30 degrees, and I asked you for the sine of 30 degrees, the sine of 30 degrees would be whatever the opposite side length is over the hypotenuse. Now we'll get to special triangles in a second. It happens to be that this is a 30, 60, 90 triangle now, the way that I drew it. But also, if I drew two triangles in here, a small one and then a bigger one, both of these triangles would be similar, and the first point on slide 89 is trying to say, since any two right triangles are similar, well, for any two right triangles that are similar, the ratios of sides would be the same. So if I took the sine of 30 here, and took this side as opposite, and this smaller hypotenuse as the hypotenuse, the ratio of the red opposite over hypotenuse would be the same as the black opposite over hypotenuse. And we'll see when we get to special triangles why that is, but I would be increasing each side by the same magnitude if we're making the triangle bigger. And they go up proportionally in the same length, because similar triangles have sides that are proportional to one another. So if I divide opposite over hypotenuse red, I'm going to get the same opposite over hypotenuse black. The sine of 30 is always going to give us 1/2. So the ratio of the opposite over hypotenuse is going to give us 1/2. How do I get there? Well, you can turn on your calculators. First, you can check that your calculator is in the right mode. So if we go into mode, right? You want to make sure that your calculator, if you're using degrees, and you look at the fourth line, it says radian or degree. You want to make sure you're in the right mode. So right now, we're in radian mode. If I want degree, you switch to degree and hit enter. Now, on a test, when I clear calculators, your calculator automatically goes back to radian mode. So if you were to do the sine, which is right here, sine, which should give you opposite over hypotenuse, the sine of 30 degrees. If your calculator is in radian mode and you're putting in degrees, you're not going to get the right answer. So you want to make sure you're in the right mode. It's important for tests. The sine of 30 gives me 0.5. Again, you have sine, cosine, and tangent right here. You can get the reciprocal functions of cosecant, secant, and cotangent by doing 1 divided by. So if I needed the cosecant of 30 degrees, then I can do 1 divided by the sine of 30. That should give me cosecant, because they're reciprocal functions. And that gives you 2. 1 divided by 1/2 gives you 2. Right? So you guys can use your calculators to solve some of these problems. Fortunately, a lot of the problems that you're going to be getting via web work and homework won't necessarily be ones that you can just plug and chug. But that's what this tells me. This tells me if I took the sine of 30 degrees, it would give me a ratio of sides. Not that the opposite side is 1 and then the hypotenuse is 2. But it could be that this side was equal to 3 and this side was equal to 6. So the ratio of sides, 3 over 6, would give me the 1/2. This side could be a 9 and this side could be an 18. So if I took the sine of 30 here, it would be 9 over 18, which also gives me a half. So the next point on the slide, you do not always need to know the angle in order to find the answer to a question. So sometimes you'll just get a bunch of side lengths. And note, if you get a few side lengths, that's enough to solve the problem. So you don't necessarily need to know every single side length. And I give you an example here. If you have a triangle with an angle theta, and here I have a rad 5 and here I have a 3, and I want you to find the sine, cosine, and tangent of theta. Well, the sine of theta would be the opposite side over the hypotenuse. Well, here's theta. The opposite side is here. I don't know what that is. The hypotenuse is 3 though. So I'm going to put that one on hold. I'm going to put that one on ice. The cosine of theta, ca, adjacent over hypotenuse. The adjacent side is root 5. The hypotenuse is 3. So I get the cosine of theta. The tan of theta should be opposite over adjacent. So the opposite side, oh, I don't have yet. The adjacent side is root 5. So again, I'm stuck. Well, how do I get the opposite side? Here, underneath, you don't always get all 3 sides, but you can use a special rule to find the side of a right triangle given 2 sides. I'll give you a hint. It starts with a P and it ends with an Pythagorean theorem. Alright? You use the Pythagorean theorem. The Pythagorean theorem tells you, and I hate it when people say a squared plus b squared equals c squared, because then I challenge them and say, where's a, where's b, and where's c? But really, the Pythagorean theorem says that leg 1 squared plus leg 2 squared equals the hypotenuse squared in a right triangle. Important to note, only if we have a right triangle can we use the Pythagorean theorem, and it'll tell you that the legs, the sum of the squares of the legs gives you the hypotenuse squared. The hypotenuse again is the longest side. So sometimes when people say a squared plus b squared is c squared, they put the c in the wrong place. Shooting yourself in the foot there. So I want leg 1, which is rad 5 squared, plus leg 2, which I don't know, it's o. O squared is 3 squared. 5 plus o squared is 9. O squared is going to be 4. So o is 2. It's positive or negative 2, but the side length of a triangle cannot be a negative length. So not positive and negative 2, I have a side length of 2, root 5, and 3. So the opposite side is 2, the opposite side is 2. Great, I now have the sine, cosine, and tangent. If I wanted the reciprocal functions, I can flip this for cosecant, flip this for secant, and flip that for cotan. On your web work and in your textbook homework problems, you will note that 2 divided by radical 5 will not be a possible solution because your textbook likes to rationalize the denominator. So will GMATs, LSATs, CRAPATs, whatever AD exams you need to take. You need to rationalize this. We discussed how to do this in the beginning part of the semester. You multiply numerator and denominator by rad 5 in this case, right? And rad 5 times rad 5 is 5. So my numerator is 2 root 5. Okay? So that's what I have for now. Use the Pythagorean theorem. You can get the third side, and notice I was able to get the sine of theta 2/3, and I don't even know what the angle theta is. I don't know how many degrees that is. I don't know if it's 40 degrees, I don't know if it's 30 degrees, I don't know if it's 70 degrees, but I know that the sine of this angle is the opposite side over the hypotenuse, and I'm able to solve for it without knowing the angle measure. Another example, if alpha is 3/4, so they like to use Greek letters for the angle measures. Theta is one of them, alpha is another, beta is another. if cosine of alpha is 3/4, sketch a right triangle and find the cosecant, secant, and cotangent. I'm going to leave that one in your hands. It's a similar problem. They're giving us two sides. If the cosine of alpha is 3/4, you have to use that info. How are we going to do it? You're just going to say, okay, the cosine of not theta, let's call it alpha. Let's call this angle alpha. The cosine is 3/4. Cosine of an angle is the adjacent over the hypotenuse, and it's equal to 3/4. That must mean that my adjacent side is 3 and my hypotenuse is 4. Got it? So we can do a similar type of Pythagorean theorem to find the third side and then find all the trig ratios associated with it. And I'm going to leave that one in your hands. Slide 90, special triangles. Okay, these are special, all right? They're reference triangles. For any of you that took your SATs, they were on the first page of each math section that are on reference tables. I'd rather people don't flip back and forth, especially any of my high school students. I make people commit these two to memory. If you're planning on taking any of those crap out exams again, they're probably going to be on the reference tables, but why waste time flipping back and forth? There are two special right triangles. They show up all the time because in practical real-world applications, you see them everywhere. What are those two special triangles? One, it's a 45-45-90 triangle. So the 45-45-90 triangle, really favorite application on any type of standardized admissions test is you need to find the diagonal of a square. Well, what's special about squares? We know that squares have 4 equal sides. So if I don't know what the side length is, I'll call it x. Now, I also know that squares have 4 sides that are perpendicular to one another, so each angle is 90 degrees. Great. Those two pieces of info down. Regardless of what the sides of the square are, or is, what the side is, I can find the diagonal using the Pythagorean theorem. The leg squared, x squared, plus a second leg squared, x squared, should give me the hypotenuse squared, h squared. Well, what's x squared plus x squared? 1x squared plus 1x squared. Since they're both the same length, they're both x. X squared plus x squared is 2x squared. That gives me the hypotenuse squared. The hypotenuse itself would be the square root of 2x squared. And any of you that paid attention when we were reviewing chapter 1 would say, okay, I can break up a radicand that has 2 factors in it to say root 2 times root x squared, and I get x rad 2. And guess what? For a 45-45-90 triangle, the ratio of the sides is x root 2, where the hypotenuse is bigger than the side lengths. So if this was a 3, this would be a 3, and this would be a 3 rad 2. If this was a 10, this would be a 10, this would be a 10 rad 2. If the diagonal was a 10, let's say, then I would know, hey, the diagonal is a 10. Let's say, let's get rid of these 3's, not to confuse us. So if the diagonal is equal to 10, and x rad 2 is representative of the diagonal, I can divide both sides by root 2 and say x is 10 over root 2. So each one of these sides have to be 10 over root 2. And again, this is a favorite type of example on any of your graduate admissions tests. Okay? You have a side length of a 45-45-90 triangle, or they tell you a diagonal of a square. If I know 2 sides are equal, this shows up even in circles. If you have 2 radii, you have a quarter of a circle, what would the diagonal there be? You know that the ratio of the sides is x root 2, 5 root 2, 7 root 2. If the diagonal were the whole number, you divide that by root 2 and then you have one of the side lengths. That's one of your 2 special triangles. You should commit it to memory. On my typical final exams, I would ask you to perform trig ratios of specific multiples of 45 And this triangle is a lifesaver. If you don't know a 45, 45, 90 triangle and the next triangle coming up, you'd technically be screwed for the final. You're not necessarily responsible for the whole derivation, but you do need to know that the ratio of sides of a 45, 45, 90 triangle are x, x, x root 2. 30, 60, 90 triangle. Where do these things come from? Okay, so your next special triangle, and I drew it way out of proportion, is coming from a 30, 60, 90 triangle. You're again not responsible for the derivation. But let's say we had an equilateral triangle. Equilateral means equal sides. If all three sides are the same, and I'm going to call each side 2x, you'll see why in a second. If I call each side 2x, each side is the same. That implies that each angle has to be the same. So if I have three angles summing to 180, each angle has to be equal to 60. So in an equilateral triangle, each side is the same, each angle is the same. What happens when we cut this guy in half? If I cut an equilateral triangle in half, and this becomes a perpendicular bisector, or it cuts the line in half and forms a 90-degree angle, then this whole side, which used to be equal to 2x, is cut in half. So this part of the side is equal to x. This angle stays 60, this is 90. 60 plus 90 is 150. That means this angle gets cut in half and it's 30 degrees. The resultant triangle, therefore, is a 30, 60, 90 triangle, which is another special triangle. And we see for now, the side opposite 30 has a length of x, the hypotenuse has a length of 2x. What does that mean for the side that is adjacent to 30 or opposite to 60? What is that going to equal? Again, we have a special rule. Starts with a P, ends with the Pythagorean theorem, right? The Pythagorean theorem would tell us this side length x plus this side length, whatever we wanted to call it, let's call it a for now. X squared plus a squared should be the hypotenuse squared. The hypotenuse is all of 2x squared. All of 2x squared gives me a 4x squared. Subtract an x squared from both sides, and my adjacent to 30 side, a squared, would be 3x squared. If I want a by itself, I need to square root both sides. A would be the square root of 3x squared. Now again, breaking up this radicand into its two component parts or factors would give me root 3 times root x squared, or x root 3, because the square root of x squared is x. The square root of x squared is x, the square root of 3 is the square root of 3, so I get x root 3. Again, not necessarily responsible for the derivation, but you do need to know that the side lengths of a 30, 60, 90 triangle are proportional to x, x root 3, and 2x. The smallest angle, 30, is opposite the smallest side, x. The middle angle, 60, is opposite the medium side, x root 3. X root 3 is bigger than x because rad 3 is more than 1. So I have more than 1x and 1x here. So x root 3 is bigger, therefore it's opposite the 60-degree angle. The biggest side is the hypotenuse, which is 2x. Root 3 is less than 2, but more than 1. So that's why this side's in the middle. This is the biggest side, this is the smallest side. Opposite the smallest angle, opposite the medium angle, opposite the largest angle. Again, a 30, 60, 90 triangle, like the 45, 45, 90 triangle, they're both extremely important. They both show up in the graduate admissions testing. They showed up on SATs. And if we were taking a final or did have trig on our final, they would be a serious component of your final exam. So I would definitely understand this triangle here and the 45, 45, 90 triangle and what are the implications of. So let's say opposite the 30, if I knew that this was a side length of 5, for instance, opposite the 60 would have a 5 rad 3, and the hypotenuse would be a 5 times 2, or a 10. That is the implication. So I then ask you to find the sine of 30 and the cosine of pi over 4. So while I have this up, let's find the sine of 30 degrees. We had this earlier today. The sine asks me for the opposite side over the hypotenuse. So here's 30. I'm looking at this angle. I need opposite 30. That would give me an x. I had x here. The hypotenuse is a 2x. So what is x over 2x? Well, if I factor out the x's, I get a 1 over 2. And we already did that in our graphing calculators today. So we saw that the sine of 30 degrees is 1/2. If I were to beef this triangle up on steroids, it wouldn't matter. The ratio of sides are x, x root 3, and 2x. Notice I had a 5 here and a 10 here. So if it was a 5 over 10, it would be a half. If it was 10 over 20, it would be a half. The ratio of sides in a 30, 60, 90 triangle dictate x, x root 3, and 2x. So opposite over hypotenuse is a half. And you could have done this for 60 degrees. If I wanted the sine of 60, let's say. I want the opposite of 60, which is x root 3, over the hypotenuse, which is 2x. Again, the x's factor out, and I get root 3 divided by 2. So if you plug that in your graphing calculator, you'd get the decimal version of radical 3 divided by 2. That would be a problem for you because on my finals, I used to just have answers that had to be submitted in full number. So you would have to have submitted a root 3 over 2. Okay, it might be the same exact thing in your calc classes, so try your best to understand these special triangles and how to manipulate them. The next is cosine pi over 4. So if asked to evaluate cosine of pi over 4, how would you do it? Well, we have a way. Cosine of pi over 4, first, this is in radian mode. So I want to swap radians to degrees. Pi over 4 times 180 over pi. We learned about this in 6.1. Switching from radian to degrees, multiplying by my unit of conversion, that gives me 45 degrees. So I want the cosine of 45 degrees. How would I solve for that without a graphing calculator? Well, let's put up a triangle and say, okay, this is 90 and this is 45 degrees. How would I get the cosine of 45 degrees? That would be adjacent over hypotenuse. You got to say to yourself, this is 90 and this is 45. It's got to be a 45, 45, 90 triangle. Because if this is 90 and 45, only 45 is left over. And hey, I already know the ratio of sides in a 45, 45, 90 triangle. Technically, the ratio of sides in a 45, 45, 90 triangle is x, x, x root 2. So if I wanted the cosine of 45, that would be adjacent over hypotenuse. Adjacent is x, hypotenuse is x root 2. Now if you said, hey look, what if you use this 45 degree angle? Same thing, adjacent would be x, hypotenuse would be x over root 2. The x's factor out, and I get 1 over root 2. In your graphing calculator, you'd get a decimal answer. In your textbook, you'd be expected to rationalize this, and you would get root 2 divided by 2, because you multiply top and bottom by root 2. For me, either way would be accepted, 1 over root 2 or root 2 over 2. That's how you do the problem for cosine of pi over 4. Now, there is also a table in your books that has the sine, cosine, and tangent for all the popular values, 30 degrees, 60 degrees, 45 degrees. Some people go ahead and memorize that table. I hate that. It's on page 483. I'd rather you memorize both triangles and understand how to use them. That'll definitely get you further in life. But that's just my advice. What do I know? Alright? Go on to the next slide. Slide 91. Applications of trig. Your textbook has a ton of great problems. If you try any of them, the ones that I gave out for homework or web work, you always feel free to reach out to me if you don't get any. get any of the numbers. But understand the following. A triangle has really 6 parts, 3 angles and 3 sides. To solve for a triangle might mean that they might ask you to find any of the 3 parts of the triangle. So one definitional thing that I haven't given you yet, that I want to give you before we go into some of these problems, is you see a diagram drawn out. There's a hill and a person standing on the hill. I'm going to draw a very tall person, taller than the hill themselves. And let's say they're on a whatever mountain pass, and they're looking down at people in a boat. And those people in a boat are getting pooped on by birds in the sky. I know, very graphic imagery. Please forgive me, or not. But there's a flock of seagulls, and they just did their business on that person. So, what we're seeing here, right, is a typical textbook type of scenario. This person looking up at the birds or looking down at the human being, right, has a line of sight which is straight across. So my line of sight is just me looking out straight forwards, or me looking straight forwards out. This line of sight, the line between the horizontal line of my vision and the ground, that's called the line of sight. Horizontal. Now, the angle formed by this horizontal and my head when I tilt it up, or my eyes when I look upwards, this angle here that I'm going to do in red, it's going to be angle theta. This is called the angle of elevation. It's on your slides. You see it in the picture. Angle of elevation. As theta. Your books have it as alpha. I'm going to call this angle here beta. This is the angle formed between the horizontal and the line of sight looking downwards. And this is called the angle of depression. So in any of your applied math problems, when they reference angle of elevation or angle of depression, these are the 2 angles they're referring to. Angle of elevation is the angle with respect to the horizontal looking up. The angle of depression is the angle with respect to the horizontal looking down. So those angles formed are the angles of elevation and angles of depression. Okay? And these angles have specific implications. It gets very tricky sometimes because your textbook can also give you problems like, oh, there's a building that's on fire and there's somebody in the building at a specific floor and they're looking down. And the angle formed by them looking down and the building is this angle that the textbook is referencing. But that's not the angle of depression. The angle of depression would be with respect to the horizontal. So this is the angle of depression. And this angle is just the angle between their line of sight and the building. So you have to be very careful with regards to whatever the situation is calling for. But again, the angle of depression is with respect to the horizontal and you looking down, not with respect to a vertical line drawn straight down and that line of sight. So just keep that in mind. What does the problem say? From a point on the ground 500 feet from the base of a building, the angle of elevation to the top of the building is 24 degrees. The angle of elevation to the top of the flag on the top of the building is 27 degrees. Find the height of the building and the length of the flag. So I'm going to have to erase this. So from a point on the ground 500 feet from the base of a building. So let me draw out a building there's my building, 500 feet from the base of the building. So let's say this was 500 feet out. Point on the ground from 500 feet from the base of the building. The angle of elevation to the top of the building is 24 degrees. So the angle of elevation from this point 500 feet from the base to the top of the building is 24 degrees. The angle of elevation to the top of the flag on the top of the building, so apparently we have a little flagpole and a flag here, and the angle of elevation between the ground and that flagpole is 27 degrees. So this angle, the blue angle, is 27 degrees. The black angle is 24 degrees. So I'm just 3 degrees more. Find the height of the building and the length of the flag. So they want the height of the building and the length of the flag. So this is building is B, I'm going to call it, and the length of the flagpole F. I have two different scenarios here. One is a triangle with a 24 degree angle, a 500 foot base, 90 degrees here, and B. Is there a way for me to solve for the height B? Well, let's think about this. This angle is 24 degrees, this side is 500, and this side is unknown. The side that's unknown is opposite the angle. So do I have a trig ratio that relates the opposite side to the angle and the adjacent side to the angle? O and A. I do. I have two of them. I have tangent and cotangent. So if I use tangent, I know that the tangent of the angle, 24 degrees, the tangent of 24 degrees would give me the opposite side, B, over the adjacent side, 500. Well, this isn't a mystery value. You could find the tangent of 24. The tangent of 24, using your graphing calculator, if you're in degree mode, and you type in tan, which is right next to the cosine, right here, right, tan of 24 degrees gives you 0.445. That should be the ratio of sides of a tangent of 24 degrees. So B over 500 should equal 0.44522. I'm not going to write this out. I'm going to cross multiply directly. I'm just going to multiply that result by 500 to get an exact answer. And let's round to the nearest tenth. So the height of the building, B, is 222.6 feet. That's B. B is 222.6 feet. It's the height of my building. And I can get that because I have 2 out of the 3 pieces. Just because I have an angle doesn't mean I can't find the side lengths. You can find the ratio of sides because of SOHCAHTOA. The tan of an angle is the opposite side over the adjacent side. Now what about this flagpole business? Well, that's a little bit more challenging because the second triangle that I would draw has a 27 degree angle here, a 500 foot base, but the total length would not be the length of just the flagpole. It's the building plus the flagpole. That's the total height of the second triangle, of this blue, right? If I want a 90 degree angle, I can't just use this sliver of a triangle here. I have to use the whole triangle, which means this 20, and this is 27 degrees as well. I can't just say 3 degrees here, because that triangle here would not have a 90 degree angle, and then I can't use any of my trig ratios. So here I would do the same thing. The tan of 27 degrees would technically be the length of the building plus the flagpole over 500. Using my calculator, the tan of 27, by the way, you're able to use a calculator for these because it's not a 30, 60, 90 triangle or 45, 45, 90 triangle. We have a 27 degree angle here. The tan of 222.6 the tan of 27 rather, sorry, is 0.509. Then I'm going to multiply the result by 500, because we're going to cross multiply here. Tan of 27 times 500. That gives me 254.76. That's the building plus the flag. If the building was 222.6, I can subtract 222.6, which is building, from 254.76, which is building plus flag, and I get that the flagpole is equal to 32.16, or roughly 32.2 feet. So the building is 222.6 feet, the flagpole is 32.2 feet. That's how we do these types of problems. Okay? We can draw out a triangle, make sure there's a right angle in them, then see which trig ratio makes the most sense to use. Since here we're using the opposite and the adjacent sides, I'd want to stick to tangent, because the tan of an angle is opposite over adjacent, or the cotan, which is adjacent over opposite, but that involves a little bit more work, because my calculator doesn't have cotan, it has tan. I would have to use 1 divided by tan anyway for cotan. So why bother? Why do the extra work? I can do tangent, it'll be faster and simpler. That's where I end 6.2. Start with 6.3 soon. If you guys have any questions, make sure you reach out.